All right. I'm going to do um, these two problems. I'm going to do problems 4 and 5. All right. And I think I might be able to work them out on here. No, I'm going to work them out. I'm going to make. I made this really big, as you can see. My hand is huge here, or put the mouse here. You know, it's humongous, and so that'd be kind of like Godzilla-ish working it out there. So I'm going to work it out on the sheet of paper behind here. But here we go. We've got a skier. Assume the coefficient of friction with the snow is 0.1. Now this is kinetic friction, and the skier is heading down a slope at 9.5 degrees. Calculate the acceleration of the skier. Find the angle of the slope which the skier could coast at a constant velocity in degrees. Okay, so that'd be right. We want to get the slope right when he would be able to at a constant velocity. All right, these problems are not easy. These problems are not easy, and if you master them, I think you should get some, kind of kudos out of it. But if we just look at it methodically, now we can do this. So here we go. So if we just draw the pictures, look at it methodically. I'm going to make this smaller now so I can go to the thing. So we're just going to work on problem 4 here. All right. So we've got a skier going down a slope. Okay. Piece of cake. For me. I know. It's not your favorite thing to do. But anyway. And trust me, this gets, and I can get rid of that too. This gets easier. I'm telling you. So we know that the coefficient of kinetic friction is equal to 0.10. All right, so that should work. Now, we've got the skier, and we'll just treat the skier like a block, going down 9.5 degrees. I've actually drawn probably about a 30-degree angle here, 9.5 degrees, and we want to find his acceleration. Did they give us a mass? No. When they don't give you a mass, that means it's probably going to all cancel out. So here's my skier going down here. Woo, having fun. All right. Skiing down the slope here, and it has an acceleration. Here we go again. mg is going down. Normal force is going this way. We need to find all that stuff to be able to find the acceleration. So here we go again. I'm going to rotate this thing around. I know that's confusing to some folks. They want to leave it like this. That's fine. That's fine. And then you can just go, gosh dang it. You can just go like this and this, okay? And you could calculate it from there because you know that this is 9.5 degrees. But I like to do it flat, and I'm just going to draw the skier's center of mass here and have a force Fn, okay? And then they have mg is going this way. And they do have and we are going to assume it's got an acceleration going that way, but I don't put that on the actual body. I'm just going to say, okay, that's going that way. And by now, we should know. And it's got a frictional force going this way. A kinetic frictional force going this way. All right? And the kinetic frictional force, so let's take the sum of the forces in the y direction. That equals 0 because the skier is not crashing through the hill or going straight. So this is equal to the normal force. And we should be able to fill these in by now. This force right here, that down force right here, is mg cosine of the angle. All right? And the sum of the forces, and that's going down, minus mg cosine of the angle. And so the normal force is equal to mg cosine of the angle. All right? Whatever that angle is going to be. Okay? And then, real quick, we'll just say, okay, well, I'm just going to put in what the kinetic frictional force is, because that is equal to mu k times mg cosine of theta. And if you leave all your numbers out till you get done, then you'll be all right. So now it said, hey, it's got an acceleration. So I'll go, okay, well, the sum of the forces in the x direction are equal to some mass times the acceleration in the x direction, which is equal to this vector, which is mg sine, because it's the opposite angle, sine of theta. So that's positive. Mg sine of theta minus f of k. Oh, but we already said f of k is equal, the magnitude of f of k is equal to that. So take minus the magnitude of that, and we wind up with mg sine theta minus mu k mg cosine theta. And look at this. This works out great. Put max here. M's cancel. Masses cancel. And we've got ax, the acceleration, is equal to g sine theta minus mu of k g cosine theta. All right. Now, they asked the $1 million question. The second part is, what does this angle have to be for it to be going at a constant speed? The acceleration is equal to 0. Well, we'll just set this thing equal to 0 and we'll see what it is with the same mu of k. Right? They want us to keep the same mu of k. So if it's going to go down at a constant speed, we get a of x, 0 then, is equal to g sine theta minus mu k g cosine theta. All right, and so I'm going to bring this over here. So I've got mu k g cosine theta is equal to g sine theta. Oh, some cancel g, cancel the gravity. Now we're just doing algebra. And I've got mu k cosine theta is equal to sine theta. And so I want this, and this is mu k is equal to 0.1. All right. So I want this to equal. So I come up with mu k is equal to the tangent of theta. Because the sine over the cosine is the tangent. That's an old trig thing. So to find the angle, theta is equal to the inverse tangent of mu k. And that's how that one works. Okay? You see it laid out here. I put in no numbers. That's just the way that's the way it works, okay? All right, I'll make a recording of this.